Welcome to a new video in chemistry. In this video, we're going to be discussing formulas of hydrates. Hydrates are, you're probably more familiar with these than you think. If you've ever seen those desiccant silica gel beads that you get in packages, electronic packages, and even some clothing, these beads are hydrates. These beads absorb, moisture in the air. And it says don't eat them. Some people think that they're poisonous, but they're not really poisonous. I mean, in general, it's just not a good idea to eat anything that you're not familiar with, right? At worst, these would probably just dry out your mouth pretty good, but they're not really poisonous. But in any case, they are very effective at maintaining electronics and such when they're being packaged and mailed out. Okay, desiccants. So desiccants are basically a silicon dioxide form. It's a very uh, uh, sophisticated, if you will, form of sand. Okay, that's what sand is basically made out of, silicon dioxide. So what the silicon dioxide will do is that it will trap water molecules that are in the air. It'll absorb them, adsorb them. Sorry, not absorb, not with a B, but with a D, adsorb. The difference is that when you absorb something, you take it into yourself. These water molecules are not technically absorbed into the silicon dioxide, but they're adsorbed. They are added to the surface of this particular molecule. So adsorb, not absorbed. So a hydrate. The definition of a hydrate is a compound that has a specific number of water molecules bound to its atoms. So a hydrate is basically made of two components. Number one, it's made out of an anhydrous compound, and then it's made out of water molecules. You need both of those to make a hydrate. So let's take a look at a problem in the book 361, number 181. So we have a table here. Okay, I'll show you the table in just a second. It shows data from an experiment, one that you will conduct in class, to determine the formulas of hydrated barium chloride. So it's hydrated. That means that this is a hydrate. That means that water molecules are attached to barium chloride. Determine the formula for the hydrate and its name. Here's that data table. So you'll notice, well actually let's go ahead and jump in on here. That same data table is on the bottom left now. So you'll notice that the mass of the empty crucible, which is that little clay pot there, the crucible is 21.3 grams by itself, empty. And then when I add the hydrate to it, the mass goes to 31.25 grams. Now you'll notice on the chart below, it's asking us for the initial mass of the hydrate. So in order to find that out, so we put the hydrate in the crucible, we want to subtract the mass of the crucible and hydrate from the crucible itself, and that will tell us how much hydrate we actually have in there. So we have 9.95 grams of hydrate in this crucible of barium chloride. That's the hydrate we have in there. So what we're going to do next is we're going to heat this hydrate for 5 minutes. We're going to heat it up. So if you could imagine that barium chloride hydrate compound in there, as it absorbs heat, okay, as it absorbs heat, those water molecules are going to turn into gaseous molecules. They're going to evaporate. Okay, so they're going to evaporate into the air. We're going to put those off to the side there. And you notice that the new mass, after we've been heating it for 5 minutes, goes from 31.35 to 29.87 grams. So we've lost mass. And since we know that the barium chloride didn't evaporate and it's still inside of the crucible, we can take the difference of those two and find the mass of the amount of water that was in the crucible. And that comes out to be 1.38 grams of water, of H2O. And of course, we derived this number from, like I said, subtracting from the mass of the hydrate and crucible, subtracting the mass of the anhydrous. So that's now that the barium chloride has the water molecules detached from it, now we call it an anhydrous compound. So it's the anhydrous plus crucible. You subtract that from the mass of the hydrate and the crucible, and we end up with 1.38 grams of water. But you'll notice on the chart down below, it's not asking for the mass of water, it's asking for the mass of the anhydrous. Okay, so we want to find out how much of the barium chloride is left inside the crucible. So we go back to our original mass of the hydrate, which is 9.95, and we subtract the amount of water we know evaporated, and we end up with 8.57 grams of anhydrous solid. So now we know we have a dehydrated compound in the crucible, and the mass of that anhydrous is 8.57 grams. All right, now that we know, we filled out our data table. Now we're going to use this data to find the formula of the compound inside, of the original compound, the hydrate. So we need both masses of water and the anhydrous. And this is why we're going to need them, because now we're going to need to do some arithmetic here. We want to convert both of these. So when you're working with the hydrate and you're looking for the formula, you want to convert both masses into moles first. So I'm going to convert each of these grams into moles. So 1.38 grams of H2O. So I need the molar mass of H2O, which is 18. I do the math and I end up with 0.077 moles of H2O. All right, so I'm one step closer. Now I need the moles of my barium chloride, the anhydrous barium chloride. So 1 mole of barium dichloride there is 208.23. And I do the math of 857. 8.57 divided by 208.23, and I end up with 0.041 moles of barium chloride. Now, the next step in finding the coefficient for the hydrate is I compare the ratio. I do the ratio of water molecules to barium chloride. And that mole ratio comes out to 2. It's like 1.9 something, but I can pretty much round it to 2. So that 2 is important because that 2 ends up becoming the coefficient. And what that means is that for every one barium chloride compound, it can attach 2 water molecules. And this would be the formula, barium chloride dihydrate. Here's my formula, barium chloride dihydrate. Okay, so again, in order to find this particular formula, which is what the book asked me for, I need to figure out what the mass of the anhydrous, which is the barium chloride by itself, the mass of the amount of water that's attached to each of the compound. I find the mass of each. I convert both of them to moles, and then I work out the mole ratio with the water, the mole of the water always being on top, and then that mole ratio will give me my coefficient for how many water molecules are attached. Okay, that does it for our talk in formulas of hydrates. Good luck in your studying.